that combines to give you calcium carbonate, which is going to be either calcite or aramid, as a polymorph of calcium carbonate. And you have magnesium carbonate either in the form of magnesite or dolomite, shown by this formula right there. There are many other carbonate minerals that exist. They are less common, and you're not likely to come across them, but you should be aware, for example, iron carbonates or siderites as they're known, strontium carbonates giving rise to strontiumite, manganese carbonates, rhodochrosite. You guys are close enough to mineralogy that you might even remember some of these. Barium giving you witherite, lead, cerussite, and zinc giving you smithsonite. So these are all carbonate minerals, and obviously the major difference is the cation that forms and gives rise to them. So the two kind of important carbonate minerals from our perspective in terms of what we see in the rock record are calcite and aragonite, which are polymorphs of calcium carbonate. And in the upper picture we see a chunk of calcite, and this particular mineral that we see down there is aragonite. Calcite has a rhombohedral lattice, and aragonite has an orthorhombic lattice, so it has different atomic structure, but with the same basic chemistry, obviously. A fairly common occurrence in the carbonate field of the carbonate area is magnesium is a common substitute found in the atomic structure of the different varieties of calcite, and so you have slight variations in that you have what's known as high magnesium calcite, which contains a little bit more than 5% of magnesium, up to as much as 15, 20, 25% magnesium. And that category of calcite is known as high magnesium calcite. And then, as you would suspect, if that's the case, there must be something known as low magnesium calcite, and that is going to be the form of calcite that is less than 5%, or has less than 5% magnesium present in its structure. Dolomite, another carbonate mineral, the formula that's given you there, you can see the calcium and magnesium in the structure. Ideally, in a theoretical sense, should contain a 54% of calcium and magnesium. In reality, in nature, the average dolomite is somewhat unbalanced with respect to the theoretical ideal, with about 56% calcium and about 44% magnesium in structure. And the origin of dolomite is one of the interesting things in sedimentary geology. You have the basic argument as to whether dolomite can be formed as a primary mineral, or is it merely the product of diagenetic changes. And Dr. Chaffetz might talk about that on Thursday. Yeah.
So, what exactly would you call it a low magnesium that was between 20 and 40%? Okay, if it was, say, 30% magnesium and 30% calcium.
Well, it doesn't get that in a chemical sense. The ability of the magnesium, how it relates to the lattice structure, is what determines that you've got these populations that tend to be separate from each other. The different polymorphs of calcium carbonate have different stabilities, and the least stable of those is the aragonite, The next most stable is high magnesium calcite, and the most stable of all of the carbonate minerals is the low magnesium calcite. This is important in part because of what is preserved and how it is preserved in the rock record. It particularly influences the preservation of fossils. Many organisms, many invertebrate organisms that have skeletons of calcium carbonate, very often those skeletons are aragonitic in nature, but because of the instability of the aragonite, it tends to break down over time, and the aragonite is diagenetically transformed into a low magnesium calcite form. And that can often, when that happens, that can often destroy the internal structure of the original shell material. So you preserve the overall morphology of the shell, but the internal structure is often lost by virtue of the transformation into low magnesium calcite. So where does calcium carbonate form in a depositional sense? EOD, if you've been in the military recently, that would be explosive ordnance devices, but this is geology, so that is environments of deposition. Okay, so what are the environments in which carbonates form? It's important. So climate is very important. Carbonate deposition is optimal during greenhouse climate. There are two major climatic states on the planet, the greenhouse and the icehouse climates. We are currently living in the icehouse climate in a significant interglacial period of an icehouse climate, admittedly, but we are living in an icehouse climate. Carbonates, however, are most abundant in terms of their origin and formation during greenhouse climates. So if we look at the rock record, we find that there are times stratigraphically where we have a lot more carbonates in the record than other times. So for example, in the Ordovician to Devonian, there were lots of carbonate deposition, and in the Jurassic Cretaceous we see lots of carbonate deposition. And if you look at a kind of a graph of this, it's kind of a busy graph. It shows a number of things. The middle thing listed under climate shows the climate either of the icehouse, greenhouse, icehouse, greenhouse, and here we are today in the icehouse age on the horizontal axis going from old to young. So this is the Phanerozoic, the last 542 million years worth of Earth history, and you can see during the Ordovician, Silurian, Devonian, you're in greenhouse, so you'll have lots of carbonates. You have a little excursion in here where there was a cooling period that resulted in ice caps. So these are just black dots, as it were. Carboniferous, Permian, Triassic, you're in an icehouse climate, and then the Jurassic Cretaceous, you're back in the greenhouse climate. And the first slide that I had on the screen today was of chalk deposits, the white cliffs of Dover, they being Cretaceous age deposits that formed during the greenhouse climate. The lower part of the graph shows large-scale sea level changes throughout the Phanerozoic, and you'll notice that there is a relationship between high stands of sea level, low stands of sea level, high stands, and low stands. These are related in part to plate tectonic activity. And the upper part of this diagram is of interest mainly because it shows some of the extinction events or biotic crises that have occurred in the last